Hi and welcome to this second webinar about new features in EDICE 5. Today we will talk about methods to improve atrium studies and more in detail the new zone model and CFD extension. To my help I have Walter, who's a developer at Equa Simulation. He's a background in fluid dynamics or aerodynamics. And I'm Niklas, he's developing our CFD tools. And myself, I'm CEO at Equa Solutions in Sweden. My name is Max Tillberg, and I have a background, worked a lot with atriums and double skin facades. And today I will show you a number of examples how we can use this new zone model. Walter will tell you about the theory behind the zone model. Niklas will show the CFD extension. I will show an example where we compare the two models. I think that will be very interesting. And finally, in about an hour, we have some final information and Q&A session. If you have any questions, you can type them in our conference tool. And we'll try to answer them immediately if that's possible. Otherwise, we'll answer them afterwards, and this recording will be sent to you also together with questions and answers. And also, if we have time in the end, we will be able to take all kinds of questions as well. So I'm very proud to show you this. This is, well, detailed studies in atrium is something that I have requested for a long time, and it's so useful. So I will just go dig right into EDICE and show you some examples. So let's start with an atrium. So let's just import a file, an IFC file that I know includes an atrium. It's not that complex atrium, but still it's a pretty normal case. I would say. So we start with thermal comfort winter. That's usually I look at winter cases, summer cases, and then I look into the whole energy simulations. I will not do that today. So here we have the imported IFC. I convert the zone to a geometry, and yeah, here you see it. It's not that complex, but it has a complex roof shape and some triangular windows. So this is nothing we could have simulated in great detail in EDICE 4. But in EDICE 5 we have these detailed zone models. So let's look into that. So it's an atrium, big glass areas. So I think we'll have to heat it quite a bit to have good comfort. So let's say 22.5 degrees, and we need a heater. The heater, let's 10 kilowatts maybe. Make it purely convective. And I'm interested in the thermal comfort on the floor or near where people probably maybe working. So let's add a sensor plane or measuring plane, and this is, maybe you've seen that in our daylight tools previously. So we don't want daylight now, we want the new zone model. So we set up a measuring plane 1.1 meter above ground, and we want it to cover the entire space. So let's see if you can see that. Maybe you can see this sensor plane here. And yeah, we're almost done. We have the atrium, we have the sensors. Now we just need the most important thing, and that's changing to the new climate model. Here we can also increase the resolution of the grid if we want. Right now it's 0.5 meter, and we log every 4 times an hour. I want to log air temperature, operative temperatures. Yeah, I think that's good enough for now. So let's go to the simulation. So it's a winter case. So let's make it really cold, -16 degrees. We have some internal loads as well, but they will not affect that much. Just a few people in the room, and we are done. I just need to save that. And we can look at the results. So let's take a section cut, and here you can see the sensors. It's these little black things. So let's hide them. That, and we can log the air temperature, and hopefully it's a set point. And yes, it is. It's 22.5 degrees. Nothing exciting there. But let's look at the operative temperature instead, and can make it maybe 18 to, I'm guessing here, 22 degrees. And yes, so you can see here we have the effect of the cold windows in the winter, here and here and here, but still we have the same air temperature in the entire zone. So let's look into the details, and we say, okay, this is what we would have gotten from EDICE 4. It's an operative temperature of 21.5 degrees, and yeah, probably you're happy with that. But let's say that the customer wants at least 20 degrees operative temperature to make the tenants happy. So we can log that. Just press here and see that, okay, so 12 square meters of this entire zone was too cold. So let's add a radiator, and I have made that example to show you one of the most interesting features. As you're probably familiar with, radiators are always placed on walls in EDICE and all other building simulation tools that I know about. But now you can see here this little box here. That's a freestanding radiator, and that's a new thing in ICE 5 as well, that we can have people, machines, and heaters that is freestanding, but still a part of the zone model. So what I've done here is just to have this electric radiator at 10 kilowatts. 10 kilowatts for that small radiator is quite a lot, so it will be very warm. But we can look at the mean radiant. Well, let's stick with the operative temperature, and 30 degrees. And you see now that it's actually radiating in all dimensions. I think this is yeah, very useful. So let's close this one and go back to the old example. So we have the same temperature in the entire room as I've shown you. So let's look at the temperature gradient in height. So let's go into the room. We remove that plane, and instead we use measuring volume, and we say that it should be set from edges 1, maybe 6 meters high. That, so now it goes up to this height roughly, and we, instead of using the climate model, we use the new climate with stratification. So here EDICE calculates the stratification in the room, and it also takes air currents into account, for example, downdrafts from windows, jets from ventilation, and so on. So we add maybe something else. No, I think we're happy with this. And we have a resolution of 1.5 meters in height. So we have 4 layers in height. Well, maybe 5, but 4 that we visualize. So let's run that one as well. As you see, I only run it for a single day. And here you can see the view factors. We calculated 3,800 view factors in this zone. So, sensors. So now we can say take section cuts. So let's take a section cut, maybe here somewhere, and we can look at the air temperature. And let's say we look at the air temperature at 22. I'm not sure. Degrees. Yes. Aha. So here we see a clear gradient. So we have these 22.5 degrees down here, and up to, it's hard to see, I need to change the scale slightly. Oops, yeah, so it's more than 26, 27 degrees at the top of the and if we look into the operative temperature, so now we see the effect both of the radiant temperature from the windows and the air temperature in height. So we take both these into account. So my third example is that I would like to show you a summer case, and mostly regarding solar radiation. So we go to the simulation tab, and yeah, let's choose a synthetic summer day like that, and we need to log more about radiation. So let's log illuminance. I think that's a good start. Maybe something more. We'll see. And we run that simulation. Cool. Take a few seconds. The summer simulations take a little longer than the winter cases because they are so static. I fix the outside temperature, but these takes the dynamic aspects into account. And this is probably the most important thing of these new zonals, that you can simulate days or years in very high resolution. Of course, you need to be aware of logging because you can fill your hard drive quite easily. I think, yeah. Yes, I made this mistake here, but I think that's enough. I think we need to limit just to make one simulation. Yeah. That's it tried to find the worst case scenario, so it ran a number of months, but I only want to show you 1 month right now. Okay, so let's look at the illuminance in this room. So we can, no, sorry, rerun that simulation for some reason. No, there it is, illuminance. And so you can see here is the solar radiation in the morning, and then it goes around and it comes here. So here we have illuminance levels, so it's quite high, it's 80,000 lux. And we could, if we want, show the shadow animation at the same time, so you can see that. Okay, seems to work. Very crude. It's just half a meter in resolution, but still, I think it's very useful for what I want to show you. And then we could show the operative temperature, and as you see, you don't see this pattern in operative temperatures. And the reason for this is that we don't take solar radiation into account, or at least we didn't used to. No one did. We only take the surface temperatures for the glass. But now we have in a possibility to do that. So let's go into system parameters and start add considering shockwave radiation. So let's resimulate that and see that hopefully we know we'll see both illuminance levels changing, but also the radiant temperature, and also, of course, thermal comfort, for example, PPD index. Let's take a few seconds to run that simulation. As you see, it's quite fast. I'm surprised because I haven't shown you any details what we do that, but it's quite a lot of complex simulations going on under the hood. And we log the operative temperature. Set it to 30 degrees. And yes, here we go. So you see that the operative temperature, actually, you can clearly see the solar radiation in this animation, how the sun moves. I'll show you that maybe a bit clearer, like this. And maybe in a real project, I would have increased the resolution slightly. It's just a few more things I would like to show you. The surface temperature is the same in this zone right now, but that's not necessary. I'm not sure if this is a good idea, but at least it's possible to subdivide the space further. So this is, I have done this manually by wall parts. But if you see here, let's log surface temperatures. See if that's possible. Let's change the scale slightly. Let's make it 20 to say 35 degrees. And here you also see the solar radiation heating parts of the room. This is not just the new zone model. This is also for the old energy model. So this is not actually a new feature in EDIs, but as you see, you could take this into account. So say that, okay, the floor near a window will be warm, and that will, of course, also affect the thermal comfort. But we don't have any 2- or 3-dimensional heat transfer, so you need to be aware that you cannot make these too small, probably. So my final example, I have 1 minute, is to show you an example where we have jets. So let's just open that simulation. So we have the same building, but in slightly more detail, and we have added ventilation here, and also a sensor. And this sensor, it can be placed anywhere you want in the room, and this sensor can be connected and measure all these things that I've shown you. For example, we can control this underfloor heating with this air temperature, and also the operative temperature from the occupant. We can sense that, or we can make our own custom simulation, custom control system by just choosing that one, maybe some kind of control, proportional controller maybe, this one, and there is the sensor, the air temperature, and we can control the heating signal to the underfloor system. But what I would like to show you is also possible to calibrate these inlets, these supply. I will take 1 more minute, and we can do that by I can show you the product. It looks like this. So we have from the manufacturer, we have the airflow, we have the size, we have at 5 meters here, we have an airflow at airspeed at 0.3 meters per second. So what we did was that we added a box like this with this inlet, and we also just tried different sizes in EDIs with a given airflow, 33 liters per second, and simulated that. I can show you how it's done. Just show it in 3D. I'll show the air velocity, and here you can see the air velocity, and then we can limit it to 0.3. And if you look carefully down in my right down corner, we see that we have 4.92 meters away, and according to manufacturer's data, that was 5 meters. So then we know that, okay, this inlet will work, and we could add that into our simulation model, and that's what Niklas will show you later on, and also myself. But before that, Walter will tell you about the details in this new zone model.
So hi, as Max introduced me, I'm Walter Fornari, and I will talk about the basic idea behind the new stratified zonal model. So the new zonal model is actually a simple 1D layered final difference model. Oops, sorry. Can you see my screen? Can you see my screen?
Yes, we can see it.
Yeah, so it's based on a simple 1D layer final difference model that typically works very well in predicting vertical temperature gradients in pure displacement situations. However, now this has been augmented by considering explicitly the streams from individual flow elements. So for each flow element, we compute its path, and we compute the volume of air that is entrained along its path. So as a consequence, we find what is the net mass inflow and outflow in each layer, as well as the net injection and removal of energy. And by using this information and by evaluating the corresponding transport and balance equations, then we are able to predict the evolution in each layer of the mass flow, the temperature, the CO2 fraction, and the vapor fraction. So the flow elements that we have implemented right now are the jets, the plumes, and the wall currents. And let's focus at first on jets and plumes. So these specific type of flow elements are tracked along their trajectories by solving numerically a set of differential equations, which tell us how the volume flow, the momentum flow, and the buoyancy flux evolve along the trajectory. And of course, these type of flow elements are tracked until they are regarded as dissolved. So until either the velocity or the volume flow or both of these variables are below a specific threshold. And as I said, due to these flow elements, we're able to deduce the mass, heat, humidity, and CO2 fluxes between all of the layers. There are some very important driving parameters that control this type of flow elements. So of course, if you have a isothermal jet, then you know that the driving parameter is the momentum flow at the origin, so at the terminal. However, when you consider non-isothermal jets and plumes, the other very important driving parameter is the specific buoyancy flux, which is basically the rate of production of wave deficiency. Another very important parameter is the entrainment coefficient, alpha, which basically is a coefficient that tells us how much air is entrained, how much air is engulfed within our developing flow element. And in IDA, this entrainment coefficient varies with the Archimedes number, so basically with the ratio between buoyancy and inertial forces. And it varies between the value for a pure isothermal jet and the value for a pure plume. And finally, another concept that we need to solve the set of differential equations is that of a virtual origin. And basically, the virtual origin is the location where a punctual source of buoyancy or momentum would generate a similar flow element to the one that we are considering. And just to be complete, we use what is known as the maximum rule to estimate this virtual origin. Of course, each of these two flow elements originates from a different, from specific room features. And when it comes to plumes, then this originates from occupants, equipments, radiators, stalls, heating cooling panels, but also from sunlit patches, which means at the locations where the direct sunlight from a window hits a surface. And in this picture, I show you a zone with a cubic stove in it that generates quite an intense plume. On the other hand, jets originate from mechanical ventilation terminals, from openings like doors, and through some leaks through which the mass flows are quite large. It must also be said that mechanical ventilation terminals can have several nozzles, which means that a single terminal may have several jets. And we should also say that these kind of flow elements can undergo wall attachment and disattachment, for example, due to the Coanda effect. Finally, the last type of flow element that we consider is the wall currents. And these are particularly important when you have an external surface, so either an external window or an external wall, which is substantially warmer or colder than the air in the room. So in such a scenario, the air that is close to this external surface would be either heated up or cooled down, And as a consequence of this, it will start either rising or sinking along the wall, therefore creating this specific type of flow element that is known as wall currents. And this is handled in the way proposed by Toggari in 1993. We also have some other very important features that were implemented in the new zone model. So for example, we have implemented the view factor library that was developed by Walton in 2002. And this is used to account for non-convex geometries and obstacles. And therefore, this let us improve the estimation of the long wave radiation between surfaces. And this library uses several algorithms. And the most interesting one is the single area integration algorithm merged with the adaptive division of our surfaces. And this algorithm is recursively calculated until a specific convergence criterion on the view factors is fulfilled. So we have a very good convergence of our view factors. And apart from this, this specific algorithm, together with the adaptive division of our surfaces, is particularly suitable when you have to calculate obstructed view factors. Finally, we have also implemented, as Max has been showing you till now, a 3D visualization grid. And in this visualization grid, we show air velocity, temperature, CO2 fractions. But we also compute and show several comfort variables and indices as they are defined in the ISO 7730. So we compute and show the mean radiant temperature, the operative temperature, the predicted mean vote, the predicted percentage of dissatisfied, and the percentage of dissatisfied due to draft. Of course, we have performed several validations, and all of these validations have typically given very promising results. So now, before concluding, let me just show you quickly some other examples. Here, I take again the same zone that I showed you before with a very intense plume that is generated by a cubic stove. But now what I want to show you is some patches, the weaker sun patches that are generated, sorry, the weaker plumes that are generated by moving sun patches, as you can see. And here instead, I show you a large open space office in which we have computed and shown the predicted mean vote with the new climate zone model. So with this, I finished, and I give the word to Niklas, who will tell you some more words on the CFD extension for IDIs.
Okay, thank you, Walter. So I will continue to tell you something about the CFD extension, and it has been around for some time and out for testing. It's still in beta state. And presently, it's not released for ICE 5, but ICE 4.8, since we have testers, 4 testers there. My part, after all this new zone model, which looks pretty much like CFD results, actually, why do we need a CFD extension? The thing is with the new zone model, with the climate model that Walter have developed, we have added sort of resolution in the vertical dimension. In CFD, we add the 2 remaining spatial dimensions in X and Y. So we have a fully 3D representation of the flow or temperature and other fields in a zone. But one important thing is that we remove the time dimension. So with CFD, we get a three-dimensional sort of, in a way, true flow field in a room or in a zone. But since CFD is so expensive, we will restrict ourselves mostly to steady state simulation. That is, we select an instant in time and perform the CFD simulation for that instant. We can do in IDIs transient simulations, but then it's the flow field that's transient. The boundary conditions that we grab from the IDI simulation as input, they are still steady state. But what benefits do we have from running this more expensive CFD simulation is that you can include obstructions like stairways, stairs, sofas, pillars, or other things that are normally not recognized in a zone model. We can add the effect of, do we see it? Yeah, sorry. Yeah. We can have the effect of Sorry, so I'm trying to reach something. As soon as I touch anything here, it's yeah, okay, never mind. We can see effects from the selection of different supply types. In the new zone model, we can change the position, but presently the number of the sort of supply type is more limited in the new zone model than it is in the CFD model. We can also perform local flow studies. One benefit is that when we have the new zone model, we could also use the CFD to, in a sense, validate the new zone model. When we have practiced a bit with the CFD, running CFD, then we can use that as a validation tool, actually. So CFD is implemented in many softwares. The nice thing with the IDICE extension is that it's so tightly connected to the IDICE model, the zone model. And the CFD, the setup of this CFD simulation of a zone or several zones in a building, it's almost completely automated. We grab the relevant boundary conditions from IDICE, and they are automatically selected to set up the CFD simulation for the selected simulation instant. We are quite happy to have a slightly unique, I think, boundary condition treatment for heat fluxes and temperatures that sort of grabs as much as possible from the zone simulation into the CFD without constraining the CFD results too much. That is, we have a wall in a zone model has one single temperature. It's the average temperature of that wall. And we use that information, but output from CFD is a temperature distribution. We also can run the CFD case, and we can run it fully within IDICE. But I've been careful to try to implement it so that it's possible to run as a standalone CFD case as well, because there are experienced OpenFOAM or CFD users who'd like to experiment with the cases in the way they are used to. So we can export the case from IDICE and continue run it sort of in command line mode or uncoupled from the IDICE case. Another important feature we have is, this is only IDICE, a benefit from IDICE actually, is that since IDICE is a fully dynamic simulation of the building, we will get effects from internal masses into the CFD automatically. So showing here is the internal masses, the energy stored in internal masses and walls is the green areas here, and that has a huge influence if we select a time for CFD simulation. So if after a cold night the walls are still very cold, and during the morning this heat will be sucked from the zone, and we will sort of get that in the CFD mode. A bit of background, still under development as always things are, but the CFD model, as many of you have heard probably, it's based on the OpenFOAM, open source CFD tools from the CFD Foundation. We have written an interface between IDICE and OpenFOAM and C++ and the IDICE code. And the source code, since OpenFOAM is open source, it has a certain license that sort of requires us, and we also want to, we are also sharing the source code, the OpenFOAM source code that we use, for instance, the implemented boundary conditions and so forth. So that for license users, the entire source code for the OpenFOAM development we do is available. My next step here is to show you a quick, very short walkthrough. I think I have like 5 minutes of how this works in CFD. So I will start out with a standard box office. and we want to do a CFD simulation on this. First, we have to do an iDice simulation, of course. But what maybe we want to have some geometry inside this, and we can select from our samples folder, perhaps a sofa. It will end up in the corner, and in the sofa we want someone sitting. So we select this as well. We have a sitting occupant here. This guy is sitting in the wrong direction, so I will rotate him slightly 90 degrees. And then we have to move him back. So sit there nicely. Now we have these guys, and we just move them into the zone. And see that they are positioned. So now we have an occupant sitting in a sofa, and this occupant then he is sort of, or she is should be then represent the occupancy internal load. So I give this occupant a role. I connect it to the occupant in the zone. The furniture here I can connect to furniture. I give that a furniture role because we always have furnitures in a zone. So maybe we have to move it a bit. That's there, like that. It's not, you don't have to be very careful when importing objects, but so now let's perform a simulation. I've probably forgotten something by now, but let's just perform a. Yeah, I forgot to add some nice heat. Let's just add a radiator to this one. Standard procedure. Put water radiator below window. Give it some capacity, and we perform the iDice. This is the zone simulation that with just not using the new zone model. It's the old zone model in this case. So we have the details here from the results. Then we will select some. This is probably not very interesting, but let's decide that here is an interesting time to look at using CFD at 2 o'clock in the afternoon. And I will then go to the CFD tab. I select my heating simulation. I select my zone, the zone I want. I can have several of these. And I select my instant or time for CFD 2 o'clock in the afternoon. And here we see the boundary conditions coming from iDice. We can look at the temperature, surface temperatures from iDice, slightly warmer radiator there, colder window. We can also visualize the airflows. And here's a supply terminal, and here's an exhaust terminal. But we have forgotten to define that in the CFD model. So let's do that. We have to specify in CFD where these are, or we should do that. We don't must do that. It's not a must, but we should do it. Otherwise, so let's add a supply terminal to the seating. So now this would be the supply terminal instead. And this one we can give some parameters. We can give it a swirl angle, for instance. It's like a swirl diffuser that should attach the flow to the ceiling using a Wanda effect. Give it a pretty strong swirl. These numbers one has to experiment a little bit and get to know them. So there we have the supply terminal with swirl. Where is my terminal? I want to see the zone window at the same time, and my presentation thing is in the way. So how do you? Yeah, okay. We also have the option to add some simple geometries that will then represent my. Like you can have a rectangular thing here. That would be like a grill or something. You can scale it. We can rotate it. We could have a small radial diffuser. We can have a pipe, for instance, that's sticks into the domain somewhat. Then we have to scale it down because now it's a huge pipe with a huge thing. But for now, let's disable this and keep this swirling interface, swirling supply table. And then let's just to know where it is, let's put the exhaust terminal there. And now we should be ready to, I think, to perform the CFD simulation, which is more, it's just a matter of pressing. Yeah, I should, since this is a demonstration, I'll make a really coarse simulation with the large cells. Otherwise, it will take a long time. So the smallest cells that I allow here is 5 centimeters. That's too large for a serious simulation, but for now. And the largest cells is 40 centimeters in this zone. So let's just try to simulate it. First thing, it sets up the CFD case and then creates a mesh. A mesh is it's the discretization of the entire zone into, in this case, like 100,000 small, what we call cells, or mini zones. We can see here we arrived at 62,000 cells, and we had a mesh warning, but that's usually not a problem. And now the solver is running, which we can see in this counter, and also that the resulting boundary integral values shown in this table are updated, and we can see that they should be similar to the input, but they should not be. They are not identical because it's based on a different model with input from this model. Okay, so we have made some iterations. Normally we would let this go with a finer mesh for about 1,000 or 2,000 iterations. I will stop it now, convert it into a visualization format, and now we can use. So first, in the 3D view here, we see that we have a mesh. It's a volume mesh, so the entire thing is filled with these cells. And we can show, for instance, air temperature on the surface. So we see the radiator has some hot plume rising up here. We do not see much effect from the inflow. Maybe I forgot something there. But let's have a look at the inside in the volume. Out of time. Yes, actually, I forgot to update the simulation, so my nice swirling in that is not taken into account. It was I needed to do some refresh. Anyway, we see the inflow in this case from the default supply that still remains. Slight error on my point. But that was my demonstration on how the CFD model, how you work with the CFD model. It's quite simple, actually. If you have very complex models, you will have extremely large tables here. Let's see, how much time do I have? I've spent about 10 minutes, right? I can just quickly show the Atrium case. In this case, I will not run this. Here we can see that I have added, let's like this. It's upside down. Yeah. So here I have selected to create some jets, supply terminals, the ones that Max showed. Now here we have a pipe diffuser and we have a jet nozzle. So this is actually a geometrical supply that will be meshed and discretized in the CFD model. Otherwise, in this model, I have not imported any stairs or anything, but let's just show the. So now we can, if we set this to a very coarse simulation, we see that we have the boundaries here. It's a lot of them, and here we can visualize it as we did previously. The surface temperatures, and we could actually just run this, and it will take with this extremely coarse mesh. It might work. But it will be at least pretty quick. So again, the case is generated on the disk, and the entire atrium is decomposed into small cells distributed on into this. And now I'm running on 6 processors on the computer, and soon the solver will be starting. So I think that I will have to end there, actually, just showing that the simulation actually runs. My time is up, and I thank you. I leave the word back to Max.
Thanks a lot, Niklas. So I would just like to show you the difference between these two models that Walter and Niklas showed you. So let's start with the Atrium case for the winter. So if Niklas had run this simulation to convergence, we can see the model to the SONMA model to the left here on my screen, and to the right we have the CFD case, and they are, as you can see, the gradient is very similar. You have about 20.5 degrees down here, and we have a slightly warmer at the roof. It's just 1 degree, and you can see the plumes. We got one question: can we calculate plumes from persons? Yes, you can see them. This is in the CFD case, and you can see the convective heat from the persons, and here you can see them in the new SON model. You can also see the 3 jets, 1, 2, 3 here, blue dots in both models. So I feel very happy. Of course, if we look at the airflow, that was another question we got. Can we calculate downdraft at windows? Yes, we can. You can in the new SON model. You can see it here in both models. So these here you can see the warm entrance. That's why we don't have the temperature here, and here we have it over the entire facade. And you can see the jets coming here, the blue, the greenish things, and also the plume from the persons. And you can see similar in the CFD. You can clearly see the plumes, the jets. You can see the plume, and you can see these corners when you have this downdraft. The biggest difference, I would say, is this. You can see on the floor you have a big swirl in the entire room. It's not very fast. It's quite slow. It's lightly blue, but that's not visible, and you cannot see things like that in the new SON model. We also got a question about does these plumes affect each other? And in the new SON model, and no, they don't. So I guess you should avoid designing cases where they can crash into each other to maybe enhance each other. But in CFD, definitely. So this is a limitation in the SON model. We are, well, not me, but EQUA is working on it. But I guess that is not trivial to solve as fast as we want, and also to all these possible cases. So yeah, if that's the case, you should definitely stick with CFD. And for the summer case, you see much bigger gradient. Here is about 31 degrees near the roof, but it's very similar in both CFD and in the new SON model. And as far as I knew, these models were not in any way made to be similar. They were made to be identical, yes, with identical input, but they were not tweaked so they would be similar. That was just, I guess, pure luck or something. No, but I definitely think this is very convincing that we can use these. It's not CFD, but it's you still can see lots of things that was impossible before. So before questions and answers, we have a few questions. I will just mention that we will have another webinar, the second in these detailed webinars about climate-based daylighting in February 23rd. So I hope you join us then. It will also be very interesting because, yeah, it's lots of new stuff there as well. And now I have already seen a few questions, and maybe you could raise your hand if you have any other So I will just see where we are in the question here. And we have quite a lot of time. We have almost 10 minutes before 9. So that's nice. Maybe I could mention a few of them that I got here. I got a question why I did not use the climate with stratification in the first example. And yeah, that was mostly because of speed and simplifying the model, just to show that we have two new zone models. We have the one with stratification and the one without. And the big difference is, of course, these flow elements and the stratification model. But the radiation model is identical in both of them. So I try to show you both. But in a real project, I would probably use stratification since it's a nature. I know I will have stratification. I got a question about resolution. If that was fixed to 0.5 meter, and no. It can be any number in vertical and horizontal, but I choose 0.5 meter because that was it's faster to simulate. Mostly due to the not that much about space, but it takes a lot of memory also to save all this data in high resolution. But probably in a real project, I would have used a denser grid. And then, as I said, can we model plumes about groups of persons? Yes, definitely. And downdraft new walls? Yes, definitely. That's probably one of the most important things in this new zone model. Then
we have a couple of raised hands.
Yeah, great.
So I'm going to give the word to Gustav Turesson first. So I'm going to unmute you.
Do you hear me now?
Yes, yeah. Hi.
Okay, so in the new zone model, can you simulate how the downdraft is affected by, for example, a shelf sticking out from the facade? Or do you have to do that in the CFD model?
If the shelf is a part of the wall, and then I guess it has to be quite big. Walter, what do you say about that example?
Well, actually, the wall. Well, you should try to introduce a wall part and make it thicker, so maybe something different would see. But I mean, the wall current, I probably would not be stopped by the. I mean, it doesn't get stopped by something.
No. And if you made a small floor up on the wall, if you merge two zones and.
Yeah, well, then in that case, you would have two different surfaces that generate wall parts, but anyway, it's still in one dimension, so you won't block the. It won't block the current.
So
I mean, for this kind of things where you really want to see the 3DFS, then you should use CFD.
Yeah, thank you.
I would say yes, small details. It's not what we are aiming at right now. You saw the staircases, for example, in the IFC import, but that was not used in the actual simulations. That was just to make it look more interesting. So things, if we would have included the staircase, I would definitely go on with CFD as well. Or maybe divide it into a few big zones or big surfaces, but not in that level of detail. Yeah.
Yes, we have one more raised hand from Renar Miller. So I'm going to unmute you.
Hello. So I've been using NightEyes for a while, but actually I haven't seen how to activate this subdivide function for surfaces. And the second question is if the results for this subdivide functions is different temperatures for different patches on the surfaces, can they be used as input for CFD?
Not presently, and I think for quite some time, or maybe forever, we will stick to one temperature per wall surface. But if, well, it was wall parts, yes, then the answer is yes.
But also yes and no, I would say. They affect the CFD, yes. but I'm not sure if it's a good idea to include them if you want to use them as boundary condition for a CFD.
No. That was I was coming to. It will really make the case more prone to instabilities, because we will have in the setups phase, because we might have hundreds of extra CFD boundaries conditions that I have to treat, so to speak, in the conversion. And for a slightly larger case, that will be quite messy. So
also, there's one thing. Yeah, sorry. There's one thing that I didn't mention, and that's something called. I'm not sure what it's called, but we have a plume generated by sun patches. I didn't show you that, but we log where the sun falls on the floor.
During my presentation.
Sorry?
I showed it during my presentation.
Yes, but not in my cases. Sorry. And this, I think it's a bit tricky to combine these, both the local air temperature rise due to the subdivision and these patches. So I think you should go with one of them, I guess. But we haven't looked into that much yet. But it's an interesting scenario, because if we have very deep buildings, there will definitely be a difference in surface temperatures in that space. And also your question, this is not done automatically. I drew them as wall parts manually, just for this example.
Okay.
I guess you could
to modify my answer a bit. If you add wall parts, they will appear in the CFD model as a sort of separate surfaces. And splitting a floor in 2 or 4 wall parts is not a problem. But if you come up with a wall that has 100 wall parts, you will sort of make the CFD case a bit heavy.
I would say the obvious way to do this is just to take the radiation into account for example, thermal comfort. There, I think it's not a big thing, but as soon as you go to these plumes and CFD, yeah, you have to be aware what you're doing. Can be tricky, but still, it's very interesting that we have the possibilities. At least we had the possibilities in 4.8, but then we were bound to rectangular boxes. So this is, yeah, really.
Okay, thank you.
Thanks.
We have one more raised hand from Charles, so I'm going to unmute you.
Hi. I was wondering if the new zone model take in consideration like colors, like for different wall parts or like floors, like in order maybe to simulate trauma walls and so on.
Yep. Yes, it does. If with that you say that color affects the absorbance of the surfaces, this takes both regarding shortwave radiation. Yes, it does. So you can make a black chimney that is glassed on one side to see the stack effect.
Great.
I would probably go with CFD in a case like that, maybe, but I think it will work. I have made a few simulations for the new zone models, and yeah, so trauma walls, things like that, and of course all kind of natural ventilation, because we have improved the opening models as well, so we subdivide these as well. Maybe you saw in this example that I have an opening to a corridor, so that would be very tricky to simulate in 4.8 now, but now we can deal with that. Okay, it's 10 o'clock, and as I said, we will send this recording to all attendees, and also written answers if there were any answers at the end that was new. And yeah, thanks a lot. And as maybe you don't know, this is available as public beta, the new zone model. So please feel free and play around with it, try it out, see if you can find things that we haven't thought of, or maybe bugs, and let us know so we can fix them before the final release. And yeah, thanks Walter and Niklas as well. So hope to see you soon, at least at the next webinar.
Thank you.
Bye-bye.
Bye-bye.